Okay. So, can you hear well? Okay. So I will take you to space. I will switch the subject, and I will tell you about how we test fundamental gravity and general relativity using a technique which is named lunar laser ranging. And then I will also show you some extra material which is about the search for exolife, for life outside the Earth, in which this particular technique, laser ranging, is useful as a tool to aid the exploration. So I'm giving this talk on behalf of the rest of the team, which is located here at which is located at the laboratory. And we have two extra people who are not employee of the laboratory. One is Roberto Vittori, an ESA astronaut, European Space Agency. And then we have Pippo Bianco, who is the leader of the laser ranging station, which is located in the south of Italy. We acknowledge contributions and contracts and financial support from several space agencies, the Italian Space Agency, the European one, Galileo, which is the navigation constellation of the European Union, the Italian Ministry of Defense, and the Indian Space Agency. So I will introduce you to the technique of laser ranging, which is used to locate precisely the position of satellites in space, and also to locate the position of the moon with respect to the Earth. Then I will tell you about what we put in space in order to track the satellites or the moon with a laser. We'll tell you about the local infrastructure we have in Frascati, which is called the SCF Lab, which makes a frontier innovative characterization of the performance of these devices, laser reflectors, retroreflectors. And then I will tell you about the science program we pursue here within the infrastructure, and then what opportunities we have to install new reflectors on the moon and make new laser tracking of the moon. So the science we are trying to do is mainly general relativity. I will show you later what kinds of tests of general relativity, of gravity, we do with the lunar ranging to the moon and other satellites. And we do ranging tracking of the moon by means of reflectors which are already installed on the moon, which were brought by missions in the late 60s and beginning of the 70s by the Apollo missions of NASA and the Lunar missions by Soviet Union. So they're providing data since more than 40 years. You will see that the reflectors are passive devices, so they don't run out of power. They always work, provided that you have a laser on Earth which tracks them. We are doing a work of analysis of this data to test general relativity. And we have now a design of a new reflector, and you will see it's very different from the old Apollo and Lunar reflectors, which will allow us to improve the test of general relativity by a factor up to 100. And then we have another subclass of reflector, which are smaller. Its name is INRI, and this will be instead tracked by the laser, not from the Earth, but from lunar orbiters, satellites which are around the moon, which deploy eventual landers and rovers on the surface, but these spacecraft remain orbiting the moon, and then they can do laser tracking of other special types of reflectors that we can put on the surface. So what is the laser ranging measurement? You can do laser ranging to a satellite, an artificial satellite orbiting the Earth, and you can do laser ranging to the moon. This is an example. This is a cartoon which shows a station on the crust of the Earth, ranging with a laser to a reflector located on the surface of the moon. Okay? To do physics, to do general relativity, we want to have orbits between point-like masses. So we want to have two masses or three of mass m, little m, big M, eventually also the two masses of the moon and the Earth orbiting around the sun. We want to have the position of the center of mass, but we don't see that. We don't have access to the center of mass, so we have to make complex calculations, exploiting measurements taken from the surface of the Earth to the surface of the moon. Okay? So here we have the stations which shoot the laser, like this one. This is in Boston, USA. And two special devices which are located in outer space. Okay? So these devices, which I will show you in a minute, are called cube corner retroreflectors, or CCRs in our jargon. And we measure them by using time of flight of short laser pulses from the Earth. These devices provide a precise positioning. You can measure the distance between this point and this point at the level of millimeters. This is an absolute accuracy. It is a point-to-point measurement, but then it can be interpreted in the frame of the local terrestrial reference frame, in the framework of the Cartesian local lunar reference frame. And this is called absolute because this technique, laser ranging, is used in order to define our coordinate, Cartesian coordinate reference system for the Earth. It's a Cartesian coordinate system. It has an origin. It has a scale, unit of length. It has an orientation with respect to the fixed stars, the far quasars at the borders of the universe. Now, two of the elements of this Cartesian coordinate system, the origin and the scale, are defined almost uniquely by this technique, laser ranging. So whenever you measure anything else in space using the same technique, then you're transferring the intrinsic metrological absoluteness of the accuracy of the positioning with laser ranging to other satellites. Plus, these laser reflectors are passive. They don't need any power. They're maintenance-free, and they work virtually forever. So the idea is you have a station. You have this special mirror, the CCR, and this does not reflect as a normal mirror. If you're a mirror and look at you, then I see her face, because it's a reflection like this. The normal reflection is like this. Okay? The retroreflection is a reflection in which the ray, the light ray, the laser ray, even my eye, goes back from where it was originated. Okay? So if you look at these cube corner reflectors with your eye, you always see in the center of the reflector the center of your eye. No matter where you are, you move, you always see your eye, because it is done in such a way, as I will show you, that this does a triple reflection on the back faces, and it always goes back from where it was originated. So all these stations, this one particularly in Matera, shoots a laser to this satellite, the Laser Geodynamic Satellite, LAGEOS, and then the ray comes back. When it moves, it always gets back the tracking that you do. The same for the station in UK, the same for the station in Austria, the same for the station in the south of France. Okay? That's why they're called laser retroreflectors. So this is the idea. Because of this shape, this is the corner of a cube. If you take a cube of glass, you cut at the corner, and then you intersect this with a cylinder. Then you get a cube corner, an edge, with a circular front face. So what happens is that the laser light comes in, bounces on this face. It does total internal reflection, so it doesn't go through, but it's reflected. Hits the other face, does total internal reflection, it's reflected, hits the third face, and because of the geometric game, it goes back in the same direction. So if you look at this from here, you see here, this is my old camera. I took the picture from a very skew angle, but still I see the very center, the optical center of my camera. So in this sense, it's a retroreflection. So no matter where it is, you shoot a laser light there and you get it back. Okay, so the principle of the measurement is the following. You have a laser, you have a clock, you time the moment in which the laser pulse, short laser pulse, hits your detector here. So this is the time of the start of the time of flight. It goes through a telescope. This has very good accuracy in terms of pointing, of the order of an arc second. You direct this to either the small spherical artificial satellite you saw before, Lagos, or to the moon. On Lagos, which is filled of retroreflectors, you get the light back. On the moon, you get the light back from the reflectors which were installed by the Apollo missions, for instance. Then you get the pulse which goes back. Then it's split inside this telescope, and some of it goes to another clock, and you stop the counting of the seconds. So you have a delta time, t stop minus t start. You combine this with the speed of light, because you know that the speed of light is constant, and you get the distance. Plus you get the cosine directors, the angles of the pointing of this. So you have like a 3D vector. You know very accurately where the target was in distance and angle. Okay? So this is the principle of satellite laser ranging. Now, this is done very similarly on ground. You may have seen those who are called surveyors, or in Italy they're called geometry, in France, les géomètres. These are the people who do measurements of distances, of fields, of bridges, of airplanes, of buildings. And they put certain targets. They're called prisms. In fact, the retroreflector, the cube corner retroreflector, is a prism. Is the space version of what these surveyors use on the Earth to measure distances and shapes of things. So they put these objects on top of certain other structures, and then you use the instrument which is called the theodolite. The theodolite in order to measure the shape, the distance of the structure you are interested in. So this is like a sort of small version of the big laser station you saw before. A laser station is usually has an astronomical dome, so it's an infrastructure of 10 meters cube or less, 5 meters cube. Okay. Now this is small. It's like that. I've used it for many years. So this shoots an infrared laser from the center, the optical center of measurement of the angles. So while you look and you center your target in elevation and azimuth, so you measure the angles with good accuracy at the level of a fraction of an arc second, then at the same time you hit a button on the keyboard here, and you get a laser pulse going from the center of your optical observation to the target, a cube corner retroreflector, or another type of target which retroreflects the light. And this measures the distance back and forth and gives you an output which are either the 3 coordinates in the local coordinate system in which is centered around the theodolite, or it gives you angle, and distance. Okay? So this is, when you do laser ranging in space, is very similar to what people do already on the ground since many decades. So these are the cube corner reflectors. You see again, this is a big one. This is a very small one. These are medium size. This is 1 inch. Okay. And what you do is actually to center the airy cross that you have in your instrument with, which is literally a cross, you know, with circles in order that you center with the good accuracy optically the instrument with the symmetry of the retroreflector. Now, you see here 6 lines. This is because you have 3 physical edges, because it's the edge, it's the corner of a cube, and then you have 3 physical edges, but each one edge is reflected by the face in front of it. So you see 6, because each one of these in pairs is the physical edge on the other side reflected onto your eye. Okay, so this is again the cartoon I showed you before. Now this is a compilation of reflectors which are in space. This is again Lagos. It's the big ball. This is 6 centimeters of diameter. These are 2 of the retroreflector arrays. So it's an array, it's a matrix. 10 by 10 of reflector. So this is 100 reflectors. This is Apollo 14, and this is Apollo 11. The array for Apollo 15 is bigger. This is a smaller array of reflectors which is installed on the GPS satellites, which allows you to track very accurately the position of the GPS satellite, or of a similar Russian satellite, or a similar European satellite, which is called Galileo. And then when you use on ground the services, the radio navigation services with your car, with your boat, with your motorbike, you go around with your TomTom navigator, you receive a signal, which is the triangulation, the position that you have because of these satellites in space. But then your precision can increase if the position of the satellites in space is very well determined by using the laser tracking of the satellites. So your positioning on the ground with the TomTom does not use directly the laser ranging, but the 4 or 5 satellites that your device, your TomTom, uses in order to find its position exploits the fact that the position of the satellite in space is done very, very accurately thanks to laser ranging. Now, again, you see here that each one of these has 6 lines. 3 reflected become 6. And then that in each one of those, you see at the center the objective of the camera, which I used to take the picture. And if I move sideways, I still see the center of my camera. OK, this is a slice of the pole of this satellite, which has become an engineering model which we have here in Frascati. This comes from NASA. The first satellite, Legos 1, was launched by NASA in 1976. Legos 2 was launched by NASA and ASI, so it's an Italian-American satellite. And this is an engineering model which we have in Frascati, on which we do our testing. OK, so this is the big picture of what goes on in space. When you define the position of satellites, and when you define the so-called International Terrestrial Reference Frame or reference system. So remember, you have to imagine that this is a Cartesian coordinate system with the origin coincident with the geocenter, okay? And now we'll tell you how you estimate the position of the geocenter, which you don't see, of course. So there are many techniques, several techniques to measure the position of anything in space. One is laser ranging. Satellite laser ranging, in fact. The other one is very long baseline interferometry, which I will explain in a minute. And the other one is global navigation satellite system, which means GPS, GLONASS, the Russian GPS, Galileo, the European GPS, and so on. OK, so you see here the orbits of Legos 1 and Legos 2. Legos 1 is here, Legos 2 is here. So these are two think of it as Keplerian orbits around the Earth. The center of mass of the Earth, which is the point we want to estimate, is the focus, one of the focus, the foci of the 2 orbits, okay? So we don't see the center of mass, but we know it's the focus, one of the 2 foci of the orbit. So if we determine very accurately the orbit, point by point, using many stations, 40+ stations on the surface of the Earth, we have many segments, many 3D vectors, which show me the orbit of Legos 1 and Legos 2 in space. Then I can make a fit, mathematical fit to the orbit. And then I determine the orbit. I have the equations in 3D of the orbits. And then the geocenter, the origin of the system, is the focus, one of the 2 foci of the 2 orbits. Okay? So that's how we materialize, we define the position of the center of mass of the Earth. So it's like having a circular or elliptic ruler in space. So in space, we cannot measure distances around the Earth with a linear ruler. Put it there, and everybody sees it. That's not how it works. We have a curvilinear ruler in which everybody defines a segment or a point. Then we put everything together, and we get the orbit, an ellipse, with very low eccentricity, because the eccentricity is 0.04, of these 2 satellites is our standard ruler. You know there is a ruler in Paris which is the official 1 meter. Then this length is also replaced by a measurement of frequency of optical atomic clocks, and then we use the constancy of the speed of light in order to go from time to space. But anyway, you cannot use a linear ruler in space. You have to use an orbit which is seen by all the nations of the Earth. So, and everybody makes a measurement of a segment, and altogether define a single orbit. So In this way, by using laser ranging, we define the center of mass of the Earth. Then we also know, because we measure the distance from the crust to Lagios 2, we have an expression which relates the circumference of the ellipse to the semi-major axis. It's a pure mathematics, very simple. So once we measure with the laser this circumference, then we know what is the absolute length of the semi-major axis. So that defines uniquely in space, in an absolute way, based on the speed of light, because the laser pulse goes at the speed of light, defines the scale of length. Okay? So it's 2 elements of 3 for the Cartesian system. And then we also use very long baseline interferometry, which is a measurement of the time of arrival of the signals, of the radio signals by the quasars, which are at the border of the universe, which move very, very in a fast way away from the origin of the Big Bang. They appear as point-like, and they appear to be moving away from us without any important or significant side velocity. So in practice, they are the fixed stars. The fixed stars are the very far quasars, which are very intense sources of point-like radar radiation. So by measuring the relative arrival times of different quasars, using antennas on the surface of the Earth, which is curved, so the one which is closer to the quasar measures a shorter time of arrival. The one which is along the curvature more far away measures a longer time of arrival. And if you do an interferometry experiment between these times of arrival, using many of these antennas, big antennas on the ground, then you can determine, given that these are fixed points on the crust, how your surface is oriented with respect to the fixed stars. Those are fixed, but the Earth rotates. You do many measurements in different conditions, and then in this way you find out how you are oriented with respect to those fixed stars. And then these big antennas are located in space geodesy centers. And at the space geodesy center, you have a big antenna, which looks at the quasars, and then close to it, you have a laser ranging station. And you have other kinds of antennas, which I will tell you about, which are the GNSS antennas. So you can have the laser measure the position of the radar. So you know the relative position of the 2 types of devices, and you can collocate the measurements done by the very long baseline interferometry, which gives the orientation of the Earth, with the measurements done by laser ranging, which tell you how big is the Earth, what is the scale of length, and where is the geocenter of the crust. So by a complex calculation, which involves many stations, laser stations, geodesy stations in VLBI, you can find out the detailed shape of the crust of the Earth and their relation, the geometric relation to the position, to the unique position of the center of mass of the Earth, the origin of your reference system, which is determined by laser ranging. Now, this is not something you do in a short time, not because it's difficult and you have to do many calculations, but because you need many data spread in time in order to have all possible orientations of the Earth, in order to take into account tides, tsunamis, El Niño, La Niña, whatever, all the season. You have to average over many years and many different conditions, because the Earth is not a fixed body. There's many movements inside, outside. So once you have deconvolved all the non-point-like, non-spherical effects, then you can define the Earth as an average geoid with a certain shape, which is not spherical, with a center of mass, which is moving a bit because you have, the magma moving, the masses of the oceans moving, the moon pulling part of the oceans with a periodic effect. All these effects pollute the measurement that you want to do with the center of mass of the Earth. But in the end, over a long time, in which you take into account all the effects and their time constants, which are periodic with weekly, period, monthly. Some effects related to the moon have a period of 18.9 years, the nutation of the rotation axis of the Earth. It does a complete precession over many thousand years, but along this precession, it wobbles like that with a period which is 18.9 years. So when you do all these kind of calculations and studies, you have to take into account these time constants and wait enough that you make sure you understood and you put in the equations of motions all the possible effects. But in the end, you have a technique which intrinsically shows you, defines for you absolute position in space. That's why this adjective here, absolute, is important. It's precise because this is related to the millimeter level. With the GPS, you do decimeters. You don't do the millimeters, you do with the laser. And it's absolute because it defines uniquely the Earth center of mass, the geocenter, and the scale of length. So this is the importance of this technique. Then this technique has other shortcomings, which means negative features, which is you cannot do laser ranging when there are clouds. Light, the laser does not go through clouds. Your tom-tom instead works even if there are clouds. Radar waves go through clouds, okay? And then at the moment, the laser goes only from laser stations on the ground to satellites and the moon. There are no lasers at the moment which do the same from satellites or the moon to the Earth, okay? So all these techniques are complementary. And then once you have this definition of the center of mass of the Earth, the scale of length, and the orientation of the Earth, then you can distribute this knowledge to all the planet by means of GPS, GNSS, Global Navigation Satellite System. Because then, if you have reflectors on the satellites, which do the radio navigation for you, then in their orbit position, it's built in the knowledge of where everything else is. So it's a way to distribute the knowledge of accurate and absolute positioning in space. Okay, now, I was very slow on this first part, which is the introductory part, because you have to understand the basic ingredients. Otherwise, you will not appreciate what comes later. I will go much faster now. So this is a cartoon which shows there's a telescope, people pointing, and then this goes to Lagos and comes back. Now, the time of flight to Lagos is half a tenth of a second, 0.05 seconds. Okay? In that amount of time, light pulse goes from the crust to Lagos and back. These are the two orbits. The altitude of Lagos is about 6,000 kilometers, equal to approximately the radius of the Earth. This is satellite laser ranging. This is the same cartoon. If you do the same game with the Apollo arrays, this is Apollo 14, then the time of flight to the moon and back is 2.5 seconds. This is another, this is the pictures of the 5 arrays of reflectors on the moon. This is Apollo 11, which was installed by Aldrin and Armstrong. This is Apollo 14. You see the footsteps of the astronauts. And this is Apollo 15, 300 reflectors. Now, 2 of the rovers of the Soviet Union missions had reflectors on this device here, smaller array, but still functional. These are the landing sites of the missions, Apollo 11, 14, 15, Lunar code Luna 17 and Luna 21st, with 2 reflectors here. This other cartoon, which you can find on Wikipedia, shows you that in real time, this is a light pulse going from the Earth to the moon, 1.25 seconds, and back another 1.25 seconds, which so in 2.5 seconds, you get a retroreflection from the Apollo rays. Now, this is an example of a typical, well, this is one of the best geodetic stations in the world. This is in the south of Italy, in Matera, at the Space Geodesy Center, as I said, titled to the memory of Bepi Colombo. Now, you see here the radio astronomy, the VLBI, very long baseline interferometry antenna, which measures the position of the distant quasars and other things, other radio sources. And this is the laser ranging station. As I said, you can turn this around such that it looks at the laser station, and this can measure the position of the invariant point of the antenna. The antenna is done in such a way that when it moves, there is at least one point which remains fixed in space, approximately, because this is a big structure, so you cannot expect this many tons of steel to move without having the invariant point move at the level of 70 meters perhaps. So there is one point which is fixed. And even here, there is one point which is fixed, because this is like a theodolite. Theodolite, you set it on a tripod, you level it with the bubble, and then you move it this way, but the center of your optical observation is fixed. It doesn't move. So you have two invariant points. You have to have invariant points in order to understand where the rest of the things are moving: satellites, moon, center of mass, the crust. By the way, laser ranging was the technique which established and showed without any ambiguity that the crust is divided into plates, zolle in Italian, and these are moving like rigid bodies. Okay? If you have 3 stations on a single plate, since it's a rigid body, you know the Euler angles, and you can determine the position of a rigid body in space by 3 points. So if you measure 3 points, and there are many of these stations on each of the plates of the crust, then you can see you can see that they're drifting, they're moving. You can see, and you can measure the speed and direction of motion of the African plate, of which Matera is part, of the European plate, and these are velocities of 3 millimeters per year. Okay? And the positions. You can measure this because the laser has such a good accuracy. Okay, so the Matera Laser Ranging Observatory, MLRO, is doing also lunar ranging. This is another picture. So you see there is what I call an astronomical dome, and then this mirror. This is the mirror of the telescope. This is a 1.5 diameter mirror. This is a site in the south of France. And the site in the south of France has had, at the time of this picture, 3 lasers. One for low Earth orbit satellites, one for medium, going up to GPS, and this one for the moon. Okay? I don't know if they ever had 3 lasers operating together after they took the picture. It's not easy to maintain 3 laser ranging stations operational day and night for long periods of time. Now, this is our facility. Our facility is an infrastructure, the SCF lab, in which we design, model arrays of reflectors like this one. And then we test their thermal behavior and most of all their optical performance, their retroreflection, their efficiency for being tracked in space by studying this performance when they are in an inner space here, which is small, but it simulates carefully the space conditions. And this is done in a way that you have to create vacuum, you have to have the complete dark, you have to have also cold walls around you, because if you are in space, you see that the outer space is at an apparent temperature of 3 Kelvin, minus 270 Celsius. So this is a device which is a vacuum vessel, but also a cryogenic vessel, in which if you are inside, you see complete darkness, you feel vacuum at the level of 10 to the minus 5, 10 to the minus 6 millibars, and you also feel very cold because you have the walls inside are minus 200 Celsius. Everything is dark except for this port here, this big window, which may be opened at will. And from there, we inject inside this simulated space the solar constant, the heat spectrum of our sun. Because these reflectors are outside the satellites, they see Earth, so they see the cold space, they feel the vacuum, they feel the cold, but they also see the solar constant. And the solar constant in space is very hot. It's 1.4 kilowatts per square meter. On the ground, it's 1.0. So it's a bit hotter in space than on the ground. So it so happens that if you are in space, true, you see dark, you feel vacuum, but then your front, which sees the sun, is usually, on average, at a temperature of 300 Kelvin. Okay? Then your back, which doesn't see the sun, might be at minus 100 Celsius. Okay? So we recreate this special, faithful environment, and we test the performance of these reflectors. We move them, we let them see the sunrise, the sunset, as they see it when they are in space. So we create a very accurate simulated environment which allows us to test the performance of these devices when they are in space in order to make sure that they work and they give the expected performance both on satellites, on the moon, which is a very harsh environment, and on planets. Now, on the moon, you know that the moon, surface of the moon has nights which are long 14 days, 14 Earth days, okay? So the surface of the sun, the surface of the moon, which doesn't see the sun, is at a temperature of 60 Kelvin, okay? Minus 210 Celsius, approximately. And then during the lunar day, for 14 days, the temperature is 360 Kelvin, close to 90 Celsius. So it's a 300 Celsius or Kelvin degrees of excursion. So this is a very important, very relevant thermal effects, and you have to take that into account to make sure that your objects work. Now, in the next slides, there are more details. You see here some of the reflectors inside the two chambers. I will show you pictures, and I will show you a list of conditions, requirements, technical conditions which are necessary to make this facility, the SCF lab, work as it has to work, but I will not go through all those details because it will be too long. This is the sun spectrum, and we have 2 solar simulators which simulate the blue, which simulates the pink, up to 300,000 nanometers. This is important. Usually, many laboratories have only the visible part here to test solar panels, solar cells, and so on. But for our application, we need all the detailed spectrum up to here, the infrared, because the visible stops here at 900 nanometers with the red. Okay, so this is an example of a very large reflector array, which we built in Frascati with the Italian Space Agency, and which is aimed for Galileo, for global navigation satellite constellations. This is a picture taken with the infrared camera of the big lunar CCR, which is a 10 centimeter cube corner retroreflector, so it's mounted in a cylindrical aluminum enclosure, and this you have to understand that the tip, the corner is like that. If you mount this, and you mount the glass in the metal with some intermediate plastic in order not to break the glass and so on, you have to have points in which the glass is held by something, and if you're not careful, at that point of contact, you can have a hot spot. This can be warmer than the rest. This is a problem because if you have a piece of glass, a piece of optics, which has a thermal gradient across the body of the optics, a mirror, a telescope, a cube corner reflector, then you have a gradient of index of refraction inside the glass. And for this, if the index of refraction of the glass is not constant, as it is when it is isothermal, then the light ray, the laser light, when it goes inside the glass, it does the triple bounce and it goes back. It has to travel from the moon back to the Earth 1/3 of a million kilometers. This retroreflection can be spoiled, can be degraded by the fact that the path, the geometric path in the reflector is not correct. Then it comes out from the reflector with the wrong angle by, say, 100 microradians. 30 microradians. Then it misses Earth, or it misses your telescope. So you're here, you shoot the laser, and then the light ray comes over here. And your telescope is 1.5 meters. So you miss the light back. So you have to make sure that the shape of your reflector is correct at the level of fraction of the wavelength, 500 nanometers. Plus you have to control the thermal behavior, because if it's becoming too hot in certain spots, and then there is a too large a gradient of temperature, like 4 degrees, between the front and the inside part of the reflector, then you miss the light back. It goes elsewhere. So the thermal optical vacuum characterization we do is very important. Okay? Let me go quick. This is a list of all the requirements I told you, how that has to work, how that facility, the SCF lab, has to simulate the correct space environment. This is a paper which we wrote with the world experts, in which we defined a new standard to determine whether a retroreflector is performing well or not in space. What I told you now with the qualitative arguments, we do in a very quantitative way, and we invented, and we are patenting now, a new standard a new industry standard space test, especially for laser reflectors. This is part of the team. You see, all of them are young people in the laboratory, which is a clean room of class 10,000. Now, this is our reflector. The reflector is this piece of glass here. So it's a corner, it's a cube corner. It's the corner of a cube intersected with the cylinder with the front circular face. Then it has two inner and outer thermal shields. So in between the glass and the exterior, which is the lunar surface, or the surface of a lander in which the reflector is installed on the lunar surface, we have some thermal shields which help us to control the thermal behavior of the reflector. We have sophisticated plastic rings which interface and hold the glass. They pinch the glass above and below some glass tabs in order not to have the glass touch the metal. And then we screw all this ensemble here on this aluminum enclosure. Now, the aluminum sees an excursion in temperature similar to the surface of the regolith, the sand which you have on the moon, which is close to 300 Kelvin. So this has a very large thermal excursion. But what we want is that the gradient of temperature between the front face, the tip, right and left here is below 2 or 3 degrees. Okay? This can be very hot, very cold, but we do not want that the gradient of temperature across the body of the reflector is larger than 2 or 3 degrees. Okay? And this is in the dark. This is inside our chamber, so it's inside a special metal which is painted with a special paint, which has an emissivity. It's close to being a black body. Okay, so it's not only black, but it's also absorbs all the optical radiation, and it emits all of it. Okay, now these are measurements we did. I don't want you to look at this. The only issue, the only reason why I'm showing that is that we do very quantitative, precise measurements in which we measure the temperature profile of the glass by using the infrared camera. And then we also measure the performance, the kind of laser return we get back, both in intensity and in angular shape. We have to make sure we get back from the reflector enough intensity that it can be seen by the laser telescope also during the day when there is the sunlight, and that the direction in which it comes back is the correct one. If it goes 10 meters away, it's no good. Okay? So it's a measurement, an accurate measurement of the optical performance in shape, angular shape, and absolute density. But it's too much detail for you to follow. Instead, I want to now go to the physics, to the science, and show you that, yes, we can have a measurement of this point, from this point to this point. We have the knowledge, as I showed you before, of the center of mass of the Earth, so we can find the position of this reflector on the moon in absolute Cartesian coordinate system, which is defined, as I said, geocenter from the laser, the absolute distance from the laser, and the orientation of the Cartesian frame using the long-distance quasars, the fixed stars. Okay? So we have an international terrestrial reference frame, terrestrial, an international moon reference frame. Now, one subtle point. The Cartesian system is the system. So it would be the ITRS, okay? Origin, scale, and so on. The F is the frame. So by F, we define the coordinates, the Cartesian coordinates of all the single stations on the crust. So we don't see the axis, we don't see the origin. What we see is a realization of the system, which are the coordinates, which are well known, of all the stations on the ground. So I know that in Matera we have coordinates X, Y, Z, given numbers. So those are the ones which in practice we have. We don't have 0, 0, 0. Implicitly we have 0, 0, 0, and explicitly we have the orbits of the lasers, which are always there. They keep turning. The lifetime of the orbit is 1 million years. So don't worry, they will not fall upon us very soon. And the frame is a practical realization. And the reflectors on the moon, those are X, Y, Z in the moon system, because we don't see the Selenon center, okay? Now, the science we can do is two types of science. One is gravity, and I will tell you about that in a minute. And then there is selenodesy, which is the lunar equivalent of space geodesy, geophysics of the Earth. So the moon is a simpler body compared to the Earth. It's less active, doesn't have earthquakes, which are called moonquakes on the moon. It has moonquakes, but they're very shallow, they're very weak compared to the Earth. Still, the moon has a mantle, has a small crust, and has a core, and this is very important, it has either a liquid layer between the core and the mantle, or it has a smaller liquid core. You know that the Earth has a very solid core made of iron, which is turning, which is in practice a real dynamo, which generates a magnetic field. There is a very weak magnetic field, very weak on the moon, so the whole structure is different. And that's interesting for those who do planetary science, planetology, so to say. So we can measure tides and the composition, the internal composition of the moon from core to crust. And this is a description which makes us realize that the moon is not a point of mass m. Okay? The moon is far away, so far away from the Earth that you can consider the gravitational field of the two bodies as point-like. But if you have to do measurements using stations on the crust of the Earth and reflectors on the crust of the moon, then you have to take into account these effects. So you have to do geodesy and selenodesy. Okay? Once you have understood those effects, then you can use the center of mass of the two bodies and do gravitational physics. Okay? Now, there is a reason why, before we go to the physics, and that's the last part, there is a reason why we don't want any more, arrays. We want single reflectors. Now, the thing is that an array on the moon librates, moves, rotates, right, left, top, down by 10 degrees. So an array on the moon was installed on day 0, just facing perfectly the Earth. Then the moon librates, moves by 10 degrees. Now, when it does this, the distance from you, it increases by 150 kilometers. So it goes in a new position. After you do these measurements many times, top, down, you can take into account this and put in your equations of motion so that if you do ranging today, the array is here. If you do it in 14 days, it's over here. So you take this into account and then use the measurements in different positions and you do your fit of the position of the center of mass. However, the thing is that the array, when it's in this position, it's not facing this way. It's rigidly rotating. So when you do ranging, you don't know if you got back light from this corner, the near corner, or the far corner. Because if you get this, then you have a distance, a difference, which is the size of the array times the sine of 10 degrees. So in the case of an array which is 1.2 meters, this can be 20 centimeters, 30 centimeters, depending on the angle. So the thing moves by 150 kilometers. You can take that into account, but it also becomes oblique. So you get a time of flight which is broad. Sometimes you get the pulse back closer, sooner, sometimes later. So this, in a sense, dilutes your measurement. Since you don't know which one of the reflectors gave you the laser return, then you have an uncertainty in the measurement which is artificial. So if you instead replace the big array with a single reflector, bigger than each single reflector, then you can get almost as much as light of the whole array. But then in that case, you always know that if you get a laser return, it comes from the tip of the corner of your reflector. So you take into account that the reflector from here went here, and that's easy, it's a simple geometry. But then you have a single point retroreflecting. So you have a single point from which you get a laser return. So that simplifies a lot your measurement. And let me show you this. Let me see if I have, okay. Now, so take this, this is this plot is the time of flight. When you measure the time of flight, you measure 2.5 seconds. Okay? So suppose you subtract the 2.5, and you do that minus 2.5, so you get 0. So in principle, if you subtract that, you should have 0. But you have laser returns, which don't come at 0, but they come at sooner or later times. This is because your array is moving and vibrating in different positions. So you see intrinsically, you should see this. You should see the red. You shouldn't see a single time of flight with an error which is a millimeter, because this is plus minus 1 nanosecond. 1 nanosecond is 30 centimeters. Okay? The light makes 30 centimeters every 10 to the minus 9 seconds, 1 nanosecond. Okay? So this is an error in the position and in the time of flight of 2 nanoseconds. But this is not because the measurement of the laser is uncertain at that level. No, the measurement of the laser is good at millimeter level. This is simply because it's a geometrical effect. So you expect from geometry this, then you get something smeared, a little different, but very close. Now, Apollo 15 is big, so when it does this effect, the far corner is more far than for Apollo 11, which is smaller. Okay? In fact, for Apollo 11, you expect that this trapezoid is almost a triangle. And in fact, the shape of the data, the blue, is very similar. Okay? So in order to have those Gaussians, those distributions to be very small, with a time corresponding to 1 millimeter picosecond, you have to replace the old reflectors. You have to replace this with this. Now, this is, I will show you, it's this. So you have the glass, the thermal shields, the enclosure, and then the sunshade. The sunshade we wanted because, so this is it, okay? This is the sunshade, this is the cylinder. Inside you have this big reflector. This is the old Apollo reflector, is the big, we call it moonlight, Italian-American reflector. So this looks at the Earth, which is along the zenith, if you are at the equator on the moon, okay? So this has a weight of 1.7 kilograms. Its length is 30 centimeters. The diameter is close to 10, 15 centimeters. It depends if you take into account the diameter of the glass, which is 10 centimeters, of the rings, which is 11, 12, which is the aluminum, and then the outer diameter of the shade, which is a little less than 150 millimeters. And these are the thermal shields, which are gold painted in order to limit thermal excursions. Okay, I explained this, near corner, far corner, okay? I will go through that. Now, this is the table of measurements that we can do to test general relativity, okay? Before we go through that, which are a lot of numbers and strange names, let's look at the specific example. So the moon and the Earth are rotating in the field of the sun, okay? The sun is very massive. You can barely see it, but there is here some sort of valley which is reminiscent, which reminds you that a big mass curves space-time, okay? And we can study the motion of the Earth around the sun, and we can study the combined motion of the moon around the Earth, and both of them orbiting the sun. It so happens that if you have a satellite orbiting a bigger body like this, both masses are very much smaller than the sun. So you can, and the mass of the moon is sufficiently smaller than the Earth that this can be considered in some occasions as a two-body system. But if you consider the moon orbiting the Earth and together orbiting the sun, then you can study a very interesting three-body effect. In the sense that the moon orbiting the Earth is like a gyroscope. Okay? It's like a gyroscope. And one point which is particularly interesting in studying this gravitational system is the perigee. The perigee is the point of closest approach of the moon with respect to the Earth. And this is the apogee. Okay? What happens is that when the moon orbits the Earth, the orbit, which is elliptic, precesses around the Earth. So the perigee moves continuously. So this orbit precesses around the Earth. A similar effect is the one of the orbit of Mercury. Mercury is very close to the Sun, very, very close. It's very light. And the orbit of Mercury is also very elliptic. And this orbit precesses, does like this, and then it does like this, and then it does like this, and very quickly, because the space-time is curved, so it induces a precession on the Mercury planet. It's the Mercury perihelion precession at advancement. Now, this is a very important effect. It's a two-body effect in the case of Mercury, and it's one of the experimental effects which led Einstein to find a new theory. Because if you don't introduce the curvature of space-time, in Newtonian dynamics, you don't get any precession. In Keplerian orbits, orbits do not precess. Okay? They do in general relativity, and in the case of two-body system, Sun and Mercury, but a gyroscope, so two-body which makes a gyroscope, so a gyroscope which moves around a gravitating body which curves space-time, that also causes a precession. A precession of what? A precession of the direction of rotation of the gyroscope. So this is the precession, okay? Now, and the precession is very simple. It's, in the case of the moon, this precession here, which I said, is 3 meters per orbit. If this is the perigee, if I'm orbiting I'm the moon orbiting the Earth, now today I'm here and this is the perigee, the point of closest approach to the moon. In 14 days, sorry, in 28 days, one orbit of the moon around the Earth, the perigee will be here, 3 meters away. And then after 28 days, again, 3 meters away. Okay? So it keeps moving. And we can measure this with lunar ranging because the accuracy of lunar ranging, as I said before, is a few centimeters. And it will be close to millimeter or less if we have new reflectors on the moon. So this 3 meters is measured with an accuracy of 2 centimeters at the moment. 3 meters plus minus 2 centimeters. This is the prediction. Now, 3 is the prediction of general relativity. So the measurement we do of the precession is exactly consistent with general relativity. What we do is we subtract the exact value, 3, and we try to measure if there is any deviation. Is the perigee precession 3 meters or 3.5 or 3.3 or 3.1? So we express that in a dimensional variable, which is called KGP. So this has to be 0. And this is a certain number, which is not 0, but with an error, which is larger than the number itself. So within errors, this is 0, 10 to the minus 3. So with an accuracy of 6 per mil, we know that the precession of the moon, of the Earth-Moon gyroscope around the Sun is consistent with general relativity. It's 3 meters every 28 days, okay? Of course, if there is new physics, then this number can change. And this is a very, very important statement, because you saw from the previous presentation that fundamental physics, elementary particle physics, has a more or less consistent description, experimentally and theoretically, of the quantum forces. The electromagnetic force, the weak force, and the strong force, which is the one which is governing quarks and gluons, which together make up the hadrons, and then of special hadrons, which are the nucleons, the proton and the neutron, which make up the nuclei. Okay? Not everything is perfect in particle physics. In fact, the discoveries done at LHC recently are good. They're interesting, but they are not sufficient to complete the picture of particle physics. In addition to that, the unification of particle physics does not include gravity for several reasons. One, which is technical but also fundamental, is that all these particle physics forces can be quantized, are quantum physics. Instead, the physics we're talking about now, both the Newtonian physics and the Einstein general relativity physics, and other theories of gravity, they are non-quantistic. They are completely classical physics, we have and we deal with the point-like mass. There is no point-like mass in quantum physics. There are wave functions. There are uncertainty principles. So the description here is completely, purely mathematical, classic, in the way you study at your high school. Okay? It's non-quantum. And we know it's not perfect, but again, all the measurements we do at the moment are consistent with general relativity, which is a non-quantum theory. So there are two classes of theories which work pretty well or very well, but they're not consistent with each other. They cannot be mixed, integrated. Now, it's no problem because the moon doesn't care about particle physics and particle physics doesn't care about the moon. But if you want to have a complete understanding of the whole nature, then you need to integrate the two classes of interactions. So it's important to find how general relativity, which is a classical theory, can be overcome, expanded, extended, augmented, in order to make it a better theory which can be integrated and unified with particle physics. It's not easy, and the best thing to do is to find a measurement of a fundamental constant like the geodetic precession or other ones, which come out different from measurement compared to the prediction of general relativity, not within errors, but taking into account errors. There is one day perhaps a geodetic precession in which we find perhaps minus 1.9, 10 to the minus 3, plus minus 6, 10 to the minus 5. So the number is non-zero outside errors. Okay? So our goal here is to diminish, to lower, to decrease this number here, 6 times 10 to the minus 3. Okay? How we do that? Well, if we have current reflectors, we can take more data with more stations, which is what we do, improve our analysis and algorithms, and then we can decrease this incrementally or decrementally, slowly with time. But without replacing the reflectors on the moon now, it will be a long process. In order to make that fast, we can replace with 3 of these new big reflectors, the moonlights. Then if we do that with 3 of them, then we can improve things at a much faster pace, and then we can make, in a few years, a factor of 10 better and a factor of 100 better. So if that becomes then 10 to the minus 5, then we have the hope to find the new physics effect, which can tell us how to unify and make a better theory of gravity, and then unify gravity with the other forces. And as you see, there are at least 5 measurements you can do only with lunar ranging. There is another one and another one. So it's a very rich menu because you can do a 2-body measurement. You can test the Earth and the Moon by themselves without the Sun, and you can see if the 1 over r square law is valid or not. You can measure if the gravitational constant g, which is a constant, but it may be slowly, very slowly varying with a rate of a number in 10 to the minus 13 or 14 per year, a very, very small number. But in order to find such a small number, you have to improve your lunar ranging and then to decrease this error. Okay? So I gave you a single important example of lunar ranging physics. And like the others, this can show you where you can find a better measurement of gravity, find evaluation of gravity, and in that case, find a hint to new physics. Okay? Now, time is up, so we'll conclude. We have missions to go to the moon, and this is a lander which is under development, and we have been approved to install our reflector on this lander. Okay, so this is one flight by 2015, and this is another one in which we install the reflector on the regolith with an arm from the lander. Okay, so with this I want to conclude because we're out of time. We are studying a smaller type of reflector, which is called Instrument for Landing Roving Laser Ranging and Altimetry Retroreflector Investigations. This is something which could be installed on a small rover landing on a planet landing, for instance, on the icy moons of Jupiter and Saturn, Europa and Enceladus. And this will be tracked not by Earth, but by orbiters which are equipped with a laser on board. And let me go quickly through this. Okay, we have two missions, which are our target missions. One is the next big Mars rover by NASA. We could put this on this small array over here to be tracked from Mars orbiters. You see here the logo of the Italian, the year of Italian culture in the US. This would be a joint effort, Italy and US, so we would like to also to stamp our logo for this event, which has been extended to June 2014 on this. If this gets done and we are approved to be on that rover. And then this is another rover by ESA, the ExoMars 2018 mission. And again, here we want to put reflectors, in this case, which are tracked not by Earth, but from the laser orbiters. So this is it. I wanted to show you two classes of applications. One was the reflector on the moon, tracked by the Earth, and the other one is a smaller reflector on rovers to be tracked from orbiters which lead the exploration. Okay. Sì.